So in the next two videos, we will learn how to fine-tune a BERT model using Lightning. In this first video, we will set up the dataset and the tokenizer. So here in this notebook, we are going to load a pre-trained transformer. And then what we are going to do is we are going to adapt this transformer to a target task. So here this target task will be the same movie review classification task that we covered already in Unit 8.2, where we established the back of words baseline. So we are going to transfer this pre-trained transformer by only updating the last two layers. So we are going to treat this transformer as pre-trained, as frozen, and then we will feed it this labeled data set and update the last two layers. So let's get started here. So we will be installing this transformers library and the datasets library, which we'll be using later below. So if you don't have these libraries installed, just uncomment this and run this in the notebook, for example. And so here's our familiar watermark import, just to make sure everything is installed. And then this code here is essentially the same code that we already used previously. I actually copy and pasted it. We don't even need the count vectorizer anymore. So this is code we already used in Unit 8.2 for downloading and preparing the movie review dataset. The interesting part comes now, where we are tokenizing the dataset. So we are tokenizing it so that we can then feed it to the transformer according to what we discussed in the lecture slides. So for that, I will be using this load dataset function that I imported earlier from the datasets library here. And this one uses our CSV files. So we are using the CSV files that we created above here. And then we have this IMDb dataset class here, which we'll be using for our transformer. So the dataset class consists of a dataset dict, and this one has then these different subdictionary or dataset classes, where each one has a features list consisting of the index, text, and label, and then the entries here. And we have that for the training set, the validation set, and the test set. So this was essentially just loading the data set into this format. Now comes the real tokenization. For that, we are going to use the auto tokenizer from the transformers library here. And we are then going to train a distill BERT model, which is essentially a more efficient version of BERT. And for that, we have to have the corresponding tokenizer. So when we are training or using a pre-trained model, we have to make sure we have the right tokenizer. If we are using a distill BERT model, then we also have to make sure we use the right tokenizer that was used for pre-training this transformer. So in this case, we are using the distill BERT base model, an uncased version, which doesn't pay attention to the case, whether it's upper or lower case. And this is what we are going to also use as the model later. So here, this is the tokenizer corresponding to this model, and the model will be then also instantiated later. So what will be interesting to know about this tokenizer is the maximum length. So what is the input length for the model? And then also what is the vocabulary size? So we will also take a look at the vocabulary size. So in this case, we have an input length of 512 and we have a vocabulary of 30,000 here. So now we will tokenize the text. So for that, we will have this little utility function, tokenize text, which will operate on a batch. So this will essentially call the tokenizer here on the batch. And then we will also have some truncation to match the 512 length input. And if the input is shorter than 512, we will be padding this so that we have always this fixed length of 512. So how do we actually now use this function? So for that, we will have a map here, the map method, where we will apply this tokenize text function in a batched fashion, where we don't define the batch size here. We will be defining the batch size later on in our data loader. So this is essentially the tokenization step. It might take a bit. And then after this has finished, we can actually go ahead and delete this IMDb dataset because we won't be using the raw data set anymore, this one. So just to save some memory, we can delete that because we will be working with the tokenized version of the data set now. Yeah, and then lastly, we also have to set this to the PyTorch format. So we will set the format to PyTorch. In here it's called torch. And we will be using the columns input IDs, the attention mask, and the label column here. So the input IDs are essentially the tokenized words as we discussed in the slides. And then as the last thing, we will also be disabling the parallelism of this tokenizer. In the next unit, we will be using parallelism for the multi-GPU training of models. So we won't be using tokenizer parallelism, because if we have two levels of parallelism, parallelism for, let's say, the tokenization and the model training and the data loading, that would be a bit, let's say, too confusing, and it would also not work well with our computer, because our computer would also find that confusing. So let's disable this tokenizer parallelism. And then let's get to the interesting part, the data loaders and the model itself, of course. So the data loaders first. So we will be creating a data set now, where we will be using our tokenized version here. So the data set is relatively straightforward. We will be passing in the dataset dictionary. We will have a partition key attribute here, or argument. And then we will be accessing the partition using the partition key by accessing this dictionary. So this might look a bit confusing, but this dataset dictionary is essentially our tokenized version of the dataset. It's maybe easier to see if we have the dataset creation next to it. So we will be instantiating a training dataset, the validation set, and the test set using our IMDb tokenized dictionary. And we will have three partitions: the training, the validation, and the testing. And this is really it that we need for the data set. The only thing is, of course, using our data loader. But this is exactly the same code that we have used many times before in this lecture, where we have essentially the train data loader, the validation data loader, and the test loader here. And we will be using a small batch size of 12 because, Distilbert is quite efficient, but still on certain, let's say, GPUs, you can only have a certain batch size because otherwise we would be running out of memory. But I will share actually some additional resources with you. I wrote a blog post recently on how we can deal with smaller batch sizes. So I will share that with you in case you have memory problems. There's a little trick that we can use. Okay, so so now that we have our datasets set up, let's actually get to the most interesting part: initializing and training our Distilbert model. So let's first initialize it. And for that, we can also again use the transformers library, where we use the auto model for sequence classification class. It's quite the mouthful, but it's pretty descriptive. So we are going to import a model for classifying text here. So this is essentially somewhat similar to what we did with the Torch Hub before, where we are loading a pre-trained model. And here we are going to use the Distilbert base model, the uncased version. You are welcome to experiment with other models as well. I will share a few links where or maybe I will make that an exercise where you can experiment with other models as well. But this is a very nice model because it's relatively small and it gives you a good modeling performance. And it's a classification task where it's a binary classification task. So we have two labels, the label 0 and the label 1. So let's initialize that. It's just some warning that we should probably train this model, which we are going to do in a few moments. So, but before we do so, we mentioned in the beginning that we are only training the last two layers. In the next video, we will train the whole model. Here, we will be focusing on the last two layers. So what we have to do is we have to freeze all the layers. Remember from the transfer learning lecture in unit 7, where we used requires grad and we set it to false. It's the same thing we are doing here. We are essentially freezing here the whole model so that it's not updated during training. And then we are going to unfreeze the last layers. So for that, we have to first take a look at the model here. So taking a look at how it's structured. And what we are going to do is we will be unfreezing the last two layers here, the pre-classifier layer. It's a fully connected layer. And the last layer, the output layer, which here is called classifier. So we will be unfreezing these two layers, and then we will be fine-tuning these last two layers. So first, let's unfreeze the pre-classifier layer. It's essentially the same thing that we did above, but instead of setting it to false, we are now setting it to true here. And then we will do the same thing for the last layer, the classifier layer. So now these two last layers can be updated during backpropagation. This brings us now to the final part, the fine-tuning here. So here we will be fine-tuning, of course, the model. But for that, since the transformer works a bit differently from our previous classifiers, we have a slightly modified lightning model. So I hope it's not too complicated, but essentially there are a few modifications. First of all, the init method is exactly the same as before, but the forward method will be a little bit different. So before we usually called self model. Now we have a slightly updated version here where we have self model. We give it the input IDs, the attention mask, and the labels. So it's slightly different from what we had before. So we will have this slightly updated version. And then of course also the training step will be slightly different. So in the training step, we will now also have, of course, the inputs here corresponding to what we defined here. So we have the batch input IDs, the attention mask, and the label. And then here, of course, the loss is also retrieved slightly differently because the model returns a dictionary that contains the loss already inside. So we don't have to explicitly call the cross entropy here. And this is just how this, let's say, the Dilbert model is defined, that it returns this loss already automatically. So then we define the validation loss accordingly. It's essentially the same thing we have here for the training step, except that we swap train with validation here. But in addition to that, it might be also interesting to track the accuracy. So we will be also accessing the logits here and then calculate the predicted labels using our familiar argmax, which is something we already covered many times before, for example, in the softmax unit. Then we will be computing the accuracy using torch metrics and log the accuracy as well. So we can also visualize the accuracy after training. And analogous to the validation step, we will be defining the test step in a similar fashion here. So here we have the test step. And then we can configure the optimizer. So for the optimizer, there's nothing new here. We will be actually using Atom because it's a bit more stable for Dilbert. You're welcome to try other optimizers, for example, SGD or AtomW, but I found Atom works just fine here for this type of model. So lastly, let's also initialize our lightning model then, based on our Dilbert model. And why not? Let's also define a model checkpoint and the CSV logger so that we can log the best model after training and visualize the performance in our familiar plot. Now for the training code here, we are only training it for 3 epochs. It's actually quite the expensive model, so it will take quite some time. Notice here we are using something new. It's called mixed precision training. I found for this type of model, it will speed up the training 3 times. Also, it will be 3 times faster for this particular model if your GPU supports that. If you're getting errors, just delete that line. It will be a bit slower, but it works just fine. And I noticed that we haven't talked about mixed precision training. And this is actually a topic for Unit 9, so stay tuned for Unit 9. You don't have to use it, by the way. It will result in the same predictive performance, but it will make the training a bit faster. And for this large model, it's quite nice if the training is a bit faster. So let's actually run this and see what the results are. All right, the training is finished. Time to look at the results. So we will start with the training set performance. We will be using the best model checkpoint. And what we see is, it will take a while because it's a quite expensive model. We get 86% accuracy on the training set. Let's do the validation set next. (86) again, so no overfitting basically, and the test set. Yeah, it's 86% again, so at least our model is not overfitting. But yeah, the performance is also not that great if we think back of our baseline in unit 8.2. So in the next video, let's actually see if we can improve this by fine-tuning all the layers instead of just the last 2 layers. So in this video, we saw how we can set up the dataset and the tokenizer for fine-tuning the BERT model, which we will get to in the next video.